In the previous lecture, the regulation mechanisms have been considered for the heart function. Now it is time to study the regulation mechanisms for the circulation as a whole, and firstly, regulation of the main circulation parameter, arterial blood pressure. Regulation of blood pressure occurs through changes of both cardiac output and total peripheral resistance, or by the regulation of the heart and vessels. But first, let's consider the general classification of regulation mechanisms. And these mechanisms can be divided into systemic mechanisms of arterial blood pressure, which involves both maintaining of the existing normal regular pressure and adjustment for any changes in the body. And also there are local mechanisms of the regional blood flow regulation. The lecture focuses on the systemic mechanisms. While local mechanisms are given in your text, they are mostly descriptive, and please pay attention to reading this attentively, and if any question appear, you can ask about it. Then, systemic mechanisms. They provide regulation of arterial blood pressure. And why it's necessary to maintain and regulate arterial blood pressure. It's a key parameter of the circulation, and arterial blood pressure creates the necessary pressure difference for the blood moving through vascular system. Then, it's required for further distribution of cardiac output for each organ according to its oxygen requirement. Then, it's necessary to maintain certain level of the tissue perfusion and maintaining normal level of parameters such as oxygen, CO2 level, H+ ions concentration. These parameters are easily changed when tissue requirements, tissue activity changes, and all different organs have different level of activity at any given moment, different oxygen requirements. Therefore, you understand why blood pressure must be continually adjusted and readjusted in accordance with the oxygen requirements of the body as a whole and each tissue and organ. So it's a serious task to maintain even regular, steady level of the arterial blood pressure. Let's recall, before consideration of mechanisms of regulation, the normal blood pressure levels. We studied this already, and I hope you remember that the general level is for systolic pressure. It should be from 110 up to 139, but anything less than 120, from lower limit to 120 is considered to be optimal systolic, and systolic pressure level that exceeds 130 and comes to 139, it's already high norm. And correspondingly, the diastolic pressure level better should be less than 60 or less than 80, from 60 to less than 80, optimal level, but it can be still normal even up to 89, but it's a high norm from 85 to 89. And values 140 for systolic and 90 for diastolic are considered already hypertension. And let's consider the main factors, because regulation of the blood pressure should be directed to change the main factors that determine the level of blood pressure. And these factors, again, can be deduced from the basic law of hemodynamics. Look, volume velocity of blood movement is directly proportional to the difference of pressure, which is the moving force for blood movement, and inversely proportional to the resistance. Then we reconvert this equation into physiological type, cardiac output, which is volume velocity measured per minute. And difference of pressures, taking into account very low pressures in the end, in the right atrium close to zero, so it's simply arterial pressure, pressure in the beginning of the system. And resistance we change into total peripheral resistance. And now arterial blood pressure is located to the right side above, and if we put it to the left side of the equation, the right side look like follows. Cardiac output multiplied by total peripheral resistance. So both factors are involved into determination of the blood pressure level. Mean systemic arterial pressure depends on two factors. First, cardiac output and total peripheral resistance. These factors are easily deduced from the equation, from the basic law of hemodynamics. But it's not full list of factors. Let's recall these factors. Again, first factor is cardiac output, which depends on stroke volume and heart rate. Second factor, total peripheral resistance. These factors equally are involved into regulation and maintaining of pressure. But then there is one more factor. If you consider the cardiovascular system, not only power of motor, its motor, the heart, is important, not only resistance of the system vessels, but also the degree of the system filling with blood. The more blood fills the system, the higher becomes pressure, and with less volume of blood present inside the vessels, correspondingly less pressure is formed. And factor number 4 is the property of the blood itself, and the main factor here is the viscosity of blood. As you remember, viscosity depends on amount of red blood cells. And the last factor mostly is involved into resistance. If you remember, the equation, Poisson equation, has the blood viscosity also present in the equation. So we can consider mainly the upper 3 factors, which are very important for blood pressure maintaining. And there is a difference between two first and last factor. The first two factors can be very quickly changed because they both have nervous regulation. They have innervation by autonomic nervous system. The heart, arteries and veins, and practically all vessels that have smooth muscle cells in their walls, but of course number 1 are arterials and smaller arteries and smaller veins. They are all innervated by fibers of the autonomic nervous system. And so we can quickly change the heart function, the arteries and veins diameter, which is important for resistance. So the regulation that occurs through these two factors can be very fast. It takes seconds or maximally about a minute. So cardiac output depends on stroke volume and heart rate, and both are controlled by autonomic nervous system. I believe you remember, stroke volume depends on the force of contraction, and this is due to inotropic effect of the, it's called inotropic effect, changes of this volume by autonomic nerves. And heart rate also can be changed, and this effect of autonomic nervous system is called chronotropic effect. So both are easily changed by changes in activity of the autonomic nervous system. Then vascular resistance. It depends on the length of vessels, depends on blood viscosity, but number 1 factor, as you may remember, is the radius, because in the equation it's in the force power, and minute changes of the radius may create serious changes of the vascular resistance due to this force power. And the radius of vessels depends on degree of contraction of the smooth muscles in the walls of arteries, and predominantly on arterials. And all this depends on activity of the sympathetic nerves mostly. Or we can say tone of the sympathetic nerves, because they constantly send impulses naturally to the vessels, to the smooth muscles. So you see, both factors 1 and 2 can be changed very quickly, and they are objects of the fast regulation. So according to this classification, we can divide into fast mechanisms and slow mechanisms. The third factor, volume of the circulating blood. As you may understand, there is no nervous regulation, nervous fibers that can change volume somehow quickly. Volume, more or less, is steady, but gradual changes are possible. And these gradual changes cannot be achieved by nervous system, but can be achieved by humoral influences, some hormones. As blood volume correlates with volume of the extracellular fluid, we can expect that any loss of fluid will contribute to decrease of blood volume, and excessive fluid, extracellular fluid accumulation will mean that blood volume increases. And it depends mostly on the function of the kidney. And kidney are regulated by hormones. So time, of course, it's required, and at least hours or usually days are required to produce significant, noticeable change of the volume. But this change produces stable change of the blood pressure, because if blood pressure restoration after falling down can be achieved by vasoconstriction, this vasoconstriction cannot be maintained constantly. It's a temporary measure, but volume restoration can be much longer factor that maintains normal blood pressure. So this third factor, volume of blood, is the object of the slow regulation mechanisms. Let's follow in order. Let's start from the fast changes of circulation parameters, blood pressure fast regulation. This fast regulation occurs due to reflexes. And reflexes all begin from receptors. Then receptors send impulses to the centers, to the central nervous system, and then reflected from the center, that's why we call it reflex, the efferent changes occur which produce necessary effect. And first, but it's called the arterial baroreceptor reflex. This is basic fast type of regulation. And these reflex have the arches that consist of the afferent part, then central part, and then efferent. So three portions: sensory, central, and final coming to the vessels. So the sensory part is represented by baroreceptors and the sensory nerve. Baroreceptors we already considered for regulation of the heart, and the same baroreceptors are used for regulation of blood pressure that consists of the depends on both heart and vessels. Baroreceptors are mechanical receptors, and they respond to the pressure exerted on them and stretching degree, which is parallel changes, stretching and pressure. Stretching of arterial wall, and rate of impulses is directly proportional. Here, nu means the frequency, and delta L, stretching, or delta P, they both go proportionally. And maximal sensitivity of these receptors is for deviations from normal resting level of mean arterial pressure. Look at this figure. Here, normal pressure level appears somewhere here. It's about 100, between standard 120 and 80 for both systolic and diastolic. So this pressure, 100 millimeters, average pressure for the cardiac cycle, corresponds to the certain activity of the receptors. This mean level of activity corresponds to normal rate of impulses. So when blood pressure is normal, the receptors constantly send their impulses with the medium level of rate to the centers. And in any deviation from blood pressure, from mean normal value of blood pressure, the receptors' activity changes proportionally to the pressure. If pressure decreases just a little, there is a great decrease of receptors' rate of impulses. Oppositely, if pressure increases even a little, the activity of receptors increases greatly. You see how big decline occurs on this line. It goes within close to normal pressure limits. It's practically straight line, which shows direct proportionality between pressure and activity of receptors or rate of their impulses. So impulses are generated in proportion to the blood pressure level. Higher blood pressure corresponds to higher frequency of impulses, and less pressure corresponds to less frequency of impulses. Baroreceptors location, let me remind you, but it was considered in previous lecture, so again, let's see. These receptors are located in main reflexogenic areas. One area is aortic arch, where there is aortic body with numerous receptors, and among them baroreceptors. These baroreceptors monitor blood pressure in the entry into the whole systemic circulation. So it monitors blood supply to the whole systemic circle. But also we have the other reflexogenic zones, important carotid sinus, where carotid bodies are located. And carotid bodies also contain numerous baroreceptors as well as the other. And these receptors, for baroreceptors, they monitor blood pressure supply to the brain. So it's entry to brain blood supply. And it's important reflexogenic zone because even with normal pressure in the aorta, decreased brain blood supply with decreased pressure will be harmful for the body, and it's necessary to monitor separately the brain blood supply and its pressure. So, and from aortic arch, the fibers that go from receptors go in the total vagus nerve to the brain to medulla, and from sinocarotid area, this is sinocarotid nerve, which is a branch of glossopharyngeal nerve number 9. They both, number 10 and 9, go to medulla, to their corresponding nuclei. But finally, all these stimulate the same centers. Let's observe. So, from carotid sinus, again, sinocarotid nerve. It has also named Hering's nerve. And this is the branch of glossopharyngeal 9th nerve. From aortic arch, aortic nerve, also called depressor nerve, because it contributes to decrease of pressure. And this is the branch of cranial nerve number 10. So these nerves send their fibers to vasomotor center of brainstem. Before now, we consider that they carry, the fiber goes, these fibers go to the vagus nuclei, but as well they go to vasomotor center. Vasomotor center in a narrow meaning means exactly vessels regulating center. Sometimes they use the word vasomotor center for the general cardiovascular center. But usually we separate cardiac center and vasomotor center. Of course, it works as a single one, big center that controls the cardiovascular system as a whole. But for vasomotor center, we have differentiation of the at least two portions. The whole anatomy of vasomotor center is not fully studied, but at least we know that there are two areas with opposite functions, and it's very complexly organized. So it's located in medulla, and exactly in a part of medulla that where reticular formation passes. You remember, reticular formation received its name due to numerous connections, so that a net is formed between neurons with their connections, because so many functions should be adjusted together and coordination should occur. This complex of neurons can be divided functionally into the depressor part, and correspondingly will produce depressive reactions, decrease of pressure, and pressor part, which is responsible for higher pressure level. And of course, these both parts operate together with vagus nuclei, but vagus predominantly regulates the heart. And neurons of the depressor part produce inhibitory action of the pressor part neurons. And only the pressor part finally have efferent connections to the vessels. So vasomotor center sends impulses to the periphery, mostly through pressor part. But depressor part modulates activity and naturally decreases activity of the pressor part. But when depressor activity is less than regular, so it will produce elevation of activity of the pressor center. So efferent nerves that carry impulses from baroreceptors produce stimulation of depressor center, and as depressor center then decreases, inhibits the pressor neuron, so efferent nerves finally produce indirect inhibition of pressor part. So they stimulate depressor reactions, and it's logical. Receptors respond by elevation, by increase of the rate of the impulses, respond to higher pressure level. When pressure becomes higher, it's necessary to decrease it. So due to stimulation of depressor part of vasomotor center, these nerves produce finally decrease of pressure back to normal. Interconnection of vasomotor center. Maybe better than many descriptions to see schematic presentation of these interconnections. The vasomotor center located in medulla, and functionally we can differentiate their pressor neurons group and depressor. Exactly connection to vessels through efferent output is for pressor center in its neurons. And pressor center sends impulses down to the spinal cord lateral horns where the sympathetic preganglionic fibers are located. And then through vasoconstrictive sympathetic nerves, these impulses are sent further to postganglionic neurons and then finally to the ends of sympathetic nerves. Remember that sympathetic nerves not always, not 100% produce vasoconstriction because it depends on receptors. But predominant effect is considered to be vasoconstrictive for overall for the body. And this vasoconstriction produces total peripheral resistance. The highest degree of constriction of vessels, the higher becomes total peripheral resistance. And this is important factor for blood pressure. And plus, signs here mean that higher pressure activity makes higher vasoconstriction degree. Then higher vasoconstriction and higher resistance contributes to higher blood pressure level. So the positive influence. Blood pressure is detected due to efferent input, sensory. And we have, for detection of blood pressure, two sets of receptors located in aortic arc and in carotid sinus. These baroreceptors are stimulated by blood pressure proportionally to the level of pressure. So it's positive influence. High pressure, high activity of receptors. Then receptors send impulses through neurons, through fibers, through aortic nerve and through carotid nerve to the medulla, and the impulses finally stimulate the depressor neurons. Not always directly, but through some interconnections inside, but stimulate depressor neurons. And this is positive influence. The highest activity of baroreceptors, the stronger is stimulation of depressor neurons. And now, finally, the whole system should produce the negative feedback. And negative feedback finally is achieved by depressor neurons, which inhibit pressor neurons. And now the whole system makes the regular basis for maintaining of pressure and its regulation in case of deviations. You see, higher level of pressure produces stronger stimulation of depressor center and decreases activity of pressor, so that pressure becomes less. But decrease of pressure produces less stimulation of depressor, less than regular. Therefore, pressor is inhibited less than usual and its activity increases. So pressor center neurons produce higher stimulation of vasoconstrictive reactions, which increases total peripheral resistance and finally supports blood pressure by increase of its level back to normal. So the system is a classical negative feedback system. But of course you may understand that it doesn't go only through vascular resistance, because blood pressure depends on two factors at least for fast regulation: cardiac output and total peripheral resistance. And now it's time to combine two types of mechanism: heart regulation and vessels regulation. Let's recall efferent connections now. The efferent connections are provided by pressor neurons that send their fibers down to sympathetic centers, in particular preganglionic neurons in the lateral horns of the spinal cord. And finally, it stimulates the smooth muscles of the vascular walls of both arteries and veins. But I believe you remember the main resistive vessels of our body are arterials, because their amount of smooth muscle cells is maximal, the thickest layer of smooth muscle cells in their walls. And they are number one for regulation, for maintaining and regulation of the arterial blood pressure. But also smaller arteries have these numerous smooth muscle cells, and a little bit less, but also present smooth muscle cells are in veins, venules especially. So sympathetic fibers, as you remember, secrete norepinephrine and predominantly cause vasoconstriction. Therefore, increasing, the letter E is not correct here, but sorry, increasing the total peripheral resistance, simply increasing total peripheral resistance. The final effect of the sympathetic nerves on the vessel tone. Vessel tone, by the way, this is degree of constriction of vessel wall, which in turn depends on degree of contraction of the smooth muscle cells in walls of this vessel. And it depends, as you remember, on the type of the receptors. All receptors are adrenergic because they respond to noradrenaline, or you may say norepinephrine. But there are two opposite effects for activation of adrenergic receptors. Alpha-1 adrenergic receptors provide vasoconstriction. We studied many times this, so I show just by one line this sequence of events. Norepinephrine binds to alpha-adrenergic receptors, which results in activation of GQ protein. This Q protein, its alpha subunit, activates phospholipase C. Phospholipase C splits one of phospholipids of the membrane, producing two second messengers at once. Only one is shown here, IP3 inositol triphosphate, but it's formed always together with diacylglycerol. And it's enough to mention that just IP3 opens channels for calcium in reticulum in smooth muscles. Calcium is released, it binds to calmodulin, and the process of contraction of the smooth muscles usually becomes simply stronger, because nature they are always more or less contracted, and just degree of contraction increases. But in some organs, not alpha-1 but beta-2 adrenergic receptors predominate, and these receptors provide the opposite effect of calcium decrease, and so vasodilation. Here again the line simply: norepinephrine binding to beta-2 adrenergic receptors activates GS stimulating protein that activates adenylate cyclase. Adenylate cyclase forms cyclic AMP from ATP molecule and forms many cyclic AMP molecules. And its shortened sequence, in reality, cyclic AMP does not decrease immediately calcium level. Cyclic AMP activates protein kinase A. Actually, each 4 molecules activate 1 molecule of protein kinase A. Protein kinase A phosphorylates the certain proteins, and finally it creates the decrease of calcium in the smooth muscle cells. And please do not mix with beta-1 adrenergic receptors in the heart muscle. Heart muscle and smooth muscle, different receptors of beta type, beta-1 and beta-2. And in the heart muscle, cyclic AMP and protein kinase A activation brings more calcium into cells due to phosphorylation of calcium channels. And so calcium channels become open and much more calcium enters the cell, thus providing greater force of contraction. But this is beta-1 receptor in heart muscle cell. But beta-2 receptors in the smooth muscle cells, even in the heart vessels, in the coronary vessels, but smooth muscle cells, provide opposite effect of decrease of calcium. And relaxation follows. Less calcium, less force of contraction. So alpha-1 receptors predominantly are located in the vessels of skin, intestines, and also in kidney. And mostly we consider that generally sympathetic effects are vasoconstrictive. But in some organs, beta-2 receptors predominantly are located. Mostly this is the heart. Also somewhere in the brain, but general brain does not take part in the redistribution of blood supply. And also skeletal muscles, along with alpha-1 receptors, do have beta-2 receptors, and there can be vasodilation. So heart, skeletal muscles, and also brain have predominantly beta-2 adrenergic receptors. Sympathetic nerve tone. Now you should understand that sympathetic nerves send impulses to the vessels constantly at rest. It's rhythmical or tonical sending impulses to the vascular smooth muscles. Therefore, smooth muscles mostly are in a state of certain contraction to a certain degree. And this is basis for normal vessels tone. This vessels tone can be lost without sympathetic nerves constant discharge, constant sending of impulses. And take into account that if this impulses rate is certain value, it can be not only increased for vasoconstriction, but it also can be decreased for vasodilation as compared to normal resting state. Therefore, now you can understand why there is no need in parasympathetic nerves in the vessels with their opposite influence. we can use sympathetic nerves for both effects, vasoconstriction and vasodilation. Of course, the effect of sympathetic nerves is clearly vasoconstriction, but we can decrease activity of sympathetic nerves and there will be less vasoconstrictive effect or simply dilation as compared to initial state. So, increased tone of sympathetic nerves or increased rate of impulses. Actually, tone can be measured in rate of impulses. High frequency of impulses, constriction of vessels. Decreased tone, less than usual activity of sympathetic nerves produces dilation of vessels. In resting state, normal vessels tone is maintained by low frequency impulses. It's about 1-2 impulse per second, which corresponds to 1-2 hertz. And we can make higher frequency, can make 3, 4, 5. Actually, in sympathetic nerves, we don't have great frequencies. And at level of frequency 10 hertz, 10 impulses per second, it results in reaching the maximal degree of vasoconstriction. So the range is not great from few impulses per second. For resting state, we can increase up to 10 and it's enough to produce maximal constriction of vessels. And correspondingly decreased frequency, not 1 impulse per second, but 1 impulse per 2 seconds, per 3, per 4, so it's less than 1 hertz. It results in dilation of vessels. And again, remember which vessels mostly we mean. These are arterials and smaller arteries, as well as venules. Regulation of heart and vessels in parallel. Now it's time to combine two regulations because it enables to make changes for each individual parameter, cardiac output and total peripheral resistance, to a less degree. It's not necessary to change dramatically each one of these indices. It's enough to change each one a little, but their multiplication, their product becomes immediately changed easily. So again, arterial pressure equals cardiac output and total peripheral resistance. So depressor and pressor parts of vasomotor center operate together with vagus nuclei. They all are located nearby in medulla and they all regulate, finally, they perform one and the same regulation of the arterial blood pressure. And both are adjusted and they are combined due to action of the baroreceptors. Because the same baroreceptors that respond to blood pressure send impulses to both, for negative influence, both decreasing centers, depressor center and vagus nuclei. So it results in stimulation of changes, simultaneous changes of the heart function and vascular resistance. And it's a very efficient way of regulation of blood pressure and very fast. Let's recall the regulation of the heart through nerves. The receptors of the aortic arc and common carotid artery and carotid sinus. These receptors send impulses to the medulla through 9th and 10th nerve fibers. In the medulla, they stimulate the vagus nuclei, and vagus produces its negative effects on atria and also on both nodes and generally to the whole conductive system. Also, there is the possibility to influence the heart through sympathetic nerves, sympathetic chain, and innervated structures include all the innervated by vagus, but also ventricles, which produces difference. Also, ventricles are densely innervated by sympathetic fibers. And so, this scheme again represents regulation combined from two sides. The carotid sinus and aortic arch receptors, this sensory input provides through nerve number 9 and 10. And as I said already, that structure of the cardiovascular center not entirely clear, but at least it's well known that entry sensory input to this goes through neurons of the nucleus tractus solitarius. And in the medulla, finally, it results in stimulation of vagus nuclei, shown here to the left and named by cardiac decelerator, parasympathetic. And then Also, there is inhibition of opposite reactions of vasoconstricting. So inhibition through depressor, the inhibition of the pressor part of center. Here it's named vasoconstrictor. This is the pressor portion. And as a result, parasympathetic effects on the heart are developed, and sympathetic effects are decreased, and pressor reaction is also decreased when arterial blood pressure increases and activity of receptors increases. So all this results in efferent output. Inhibition of the heart, decreased contractility, decreased heart rate, and inhibition of contraction of smooth muscles in arterioles and veins. So there is, in response to higher blood pressure, higher than normal, we have inhibition of the heart from vagus and dilation of vessels due to suppression of pressor reaction. Both dilation of vessels and inhibition of the heart produces decreased cardiac output, decreased total peripheral resistance, and pressure becomes less and restores back to normal. Maybe the previous scheme is not very easy for reproduction, but I suggest you simply a scheme that shows interaction between centers. Let's start from parts of the center, depressor and pressor for vasomotor, and vagus nuclei for all the cardiovascular center that operates as common. So the regulated parameter is the blood pressure. It depends on the heart, its cardiac output, and depends on total peripheral resistance of vessels. Both directly proportionally determine the level of blood pressure, and both, in case of their increase, produce elevation of blood pressure, and vice versa. So this is a parameter. Then pressor center has direct connection to the vessels so that it increases total peripheral resistance proportionally to its activity. So that positive sign is here. High activity of pressor neurons produces higher degree of constriction of vessels. So it increases total peripheral resistance and finally blood pressure. Blood pressure also can be pressor center also may stimulate the heart rate, especially when activity of pressor increases. At rest, influence of the sympathetic nerves to the heart are very weak, not high, as compared to vagus, which constantly sends impulses that inhibit the heart for resting state. But blood pressure is monitored by baroreceptors, and higher blood pressure contributes to higher activity of receptors, so it's positive influence. Then baroreceptors through sensory nerves stimulate both depressor neurons and vagus nuclear neurons. And finally, we should close the negative feedback. And this feedback is closed the following way. Depressor neurons produce inhibition of pressor neurons, and vagus nuclei produce inhibition of the heart. So now we can see the whole system operates according to negative feedback principle. In a steady state, when blood pressure is perfectly normal, it creates regular normal activity of baroreceptors. Baroreceptors with usual rate of impulses stimulate both depressor neurons and vagus nuclei. Vagus nuclei therefore have their normal level of activity. A normal tone of nervous vagus produces constant regular suppression of the heart to a level which we consider to be normal heart activity and normal cardiac output. Similarly, depressor neurons inhibit pressor neurons with a certain degree of inhibition, so that resulting activity of pressor neurons is normal regular. And so impulses are sent with low frequency, 1-2 Hz, to smooth muscles in vascular wall and maintain normal tone of vessels. Therefore, it contributes to maintaining normal total peripheral resistance. And with normal cardiac output and normal total resistance, we have normal blood pressure level. Now let's consider deviations. Blood pressure increase, hypertension. And this, it's not an increase corresponding to physical activity, no, abnormal elevation of blood pressure, hypertension, and attempt to increase blood pressure even. So blood pressure increases, activity of baroreceptors becomes also higher than normal. So stimulation of depressor neuron and nuclei of vagus also become higher than usual. higher activity of vagus produces greater suppression of the heart, so that negative effects of vagus on the heart produce decrease in cardiac output. Simultaneously, depressor neuron strongly inhibit the pressor neurons, and therefore the activity of sympathetic nerves that send impulses initially produced in the pressor neurons send with less frequency, and less stimulation of smooth muscle in vascular wall produces less degree of constriction, which means practically vasodilation. Dilation of vessels means their radius increases, and according to Poiseuille equation, the total peripheral resistance decreases greatly. So resistance of vessels with the higher radius is decreased, and together with cardiac output decrease, blood pressure initially elevated becomes now decreased back to normal. Example for decrease of pressure you can observe here. Decrease of blood pressure. In this case, baroreceptors activity decreases as well, proportionally. You remember, there is a direct proportional relationship between pressure and baroreceptors activity. Then less impulses are sent to depressor, so activity of depressor neurons decreases. While it less inhibits pressor activity becomes higher with less inhibition. Also, baroreceptors stimulate vagus, but now with decreased rate of impulses, vagus nuclei are less than usual stimulated, so it decreases nervous vagus tone. So, as a result of high activity of pressor, sympathetic influences increase, and they exert on the vessels and also on the heart. And simultaneously, vagus nerve inhibits heart less than usual. What happens next? Vessels tone increases, vasoconstriction. Heart has higher sympathetic stimulation and less vagus inhibition. This all contributes to higher both stroke volume, force of contraction, and higher heart rate. Now, vasoconstriction produces higher total peripheral resistance. Increase in both stroke volume and heart rate produces higher cardiac output. And due to higher stroke volume and heart rate, you see. Both factors are main factors that determine blood pressure with fast regulation. And so, arterial blood pressure efficiently increases back to normal because cardiac output is increased and total peripheral resistance is increased. So similarly, you can produce yourself the scheme for the increase of blood pressure. Just all the arrows within the boxes should be inverted, and also the word vasoconstriction should be substituted by vasodilation. And then you just change the arrows within the boxes, and you have schematic sequence of events in case of pressure increase. So this system operates again on the basis of the negative feedback principle. Let's observe one example of such changes that can be easily explained by arterial baroreceptor reflex. This is orthostatic change of blood pressure and how it's restored. Let's recall in a line position, the pressure is created by the heart, and there is no big difference between parts of the body for the hydrostatic pressure. But just turn into vertical position, and immediately hydrostatic pressure starts to act. And let's see, from the level of the heart, if we go downward, especially to the level of legs or feet even, additionally to the blood pressure that's created by the heart, there is also hydrostatic pressure, and it's a great elevation. And while arteries have their walls that are not easily stretched, veins have much softer walls, and passive dilation occurs easily in veins, especially in lower extremities. And veins immediately become overwhelmed with blood, filled with much more blood, and they become simply dilated passively by pressure inside, by hydrostatic pressure. As you can see, volume of veins increases, and blood remains in veins, and venous return from veins, dilated veins, becomes decreased. Less blood comes back to the heart because much more blood remains in veins which are dilated. Decreased in venous return, it means that decreased end diastolic volume, according to Frank-Starling law, produces corresponding decrease in cardiac output. Heart contracts weaker and produces less stroke volume, therefore blood pressure is decreased. Decrease in blood pressure also can be noticed by the symptoms, not in healthy normal person, but people with a weaker state of health. They can suffer from the real decrease of brain blood supply because of less blood pressure at the moment. And some symptoms of darkening in the eyes can appear, the weakness, dizziness, and so on. Even fainting can occur when taking the standing position sharply occurs. So let's observe the changes that occur during this in logical sequence. First, moving from a supine into upright position, and immediately there is a decreased venous return according to described sequence of events. Decreased venous return produces decreased stroke volume, cardiac output, and therefore blood pressure. Decrease of blood pressure is monitored and detected by receptors, and less blood pressure, less baroreceptors activity. Less activity of baroreceptors, it means that less stimulation of depressor center, and pressor center activity becomes higher. Pressor center activity or tone. Practically it's measured by rate of impulses generated and sent down to the periphery. And simultaneously there is a decreased stimulation of vagus nuclei, so vagus nerve tone decreases. And what happens as a result? Activity of pressor is higher and it produces stronger sympathetic influence on arterials and veins, so there is a constriction. And decreased vagus influence on the heart means higher rate and stroke volume. So all this contributes to restoration of blood pressure which was decreased due to moving into upright position, into standing. This increase of the heart rate when there goes transition from lying into standing position is the orthostatic reflex. Look, from moving into upright position to the heart rate elevation. Description takes time, but in real body, this effect of heart rate increase comes even earlier than constriction of arterioles and veins. And the orthostatic reflex that you are going to check during classes or did already is measurement of the pulse rate before in lying position, before standing, and after standing. And naturally, according to all listed changes, we can expect higher heart rate. By the way, estimation of this increase of heart rate, change of heart rate, is from 6 to 24 beats per minute elevation. So this is a wide range for changes, and most of people fall into this range. So the increase of heart rate can be from 6 plus initial or up to 24 beats per minute plus initial. In case of increase less than 6, it corresponds to high activity predominating parasympathetic activity, and elevation of the pulse higher than 24 beats per minute testifies for predominant activity of the sympathetic system. But with balance, it should be within limits, 6 to 24. Now, we start a new type of receptors that also are involved into regulation of blood pressure. Chemoreceptors. The location of these receptors is the same. We monitor the entry to systemic circulation in the aorta and entry to brain blood supply in the carotid sinus. But receptors are not the one type. We have actually 3 parameters that are monitored, but receptor types are two types of chemoreceptors. First type is receptors that respond to the oxygen level. Oxygen level we express as the pressure, partial pressure of oxygen in blood. And so it's designated as PO2, partial oxygen pressure. The arrow down shows that receptors activity starts to be higher and higher in response to decrease of partial oxygen pressure. It's unusual. Mostly we deal with situation when elevation of parameter increases activity of receptors which respond to this parameter. But here it's unusual. Normal pressure of oxygen corresponds to normal activity of receptors. And they start to increase the activity when partial oxygen pressure decreases. It's hypoxia. Correspondingly, elevation of PO2 above normal, it's hyperoxia, will produce decrease in receptors activity. But these receptors are less numerous. Much more numerous are receptors of the second type. And these receptors respond to two factors simultaneously. And these factors are CO2 level, or partial CO2 pressure, PCO2, and H plus ions concentration. You may say also pH, but really receptors respond to ions, H plus ions, and pH is an index, logarithmic index, and know that it makes mix you everything, because pH becomes increased with less H plus ions, and it becomes it becomes lower pH when H plus concentration increases. So simply you can use H plus concentration, but it's not a mistake to say that pH is a factor that influences these receptors. So in terms hypercapnia and acidosis, we can say that are stimulating factors, because here there is direct proportional stimulation of receptors when CO2 level increases and H plus ions level increases. And when PCO2 decreases, which we say hypocapnia, and when H plus level becomes also less, it's alkalosis. In this case, receptors activity decreases as compared to normal level of activity. These receptors are considered to be peripheral because they're located in vessels, and central receptors also exist. These central chemosensitive neurons are located in medulla itself. But you should remember that there is only one type of receptors, and these receptors respond only to H plus and CO2. And even some sources may say that H plus predominantly and CO2 only indirectly. But there are no receptors that respond to oxygen level, only H plus and CO2. All these receptors also influence the blood pressure, but there is a difference. Impulses from chemoreceptors are sent through the same fibers of nerves number 9 and 10, but finally they enter the medulla, and after some connections they stimulate not the depressor neurons but pressor neurons of vasomotor center. And you logically can also understand this. When there is a deficiency in oxygen, there is excess of CO2 and H plus ions, the decrease of pressure will not help, really. It's necessary to increase pressure so that more oxygen can be supplied to tissues and easier removing of CO2 and H plus excess can occur. So, fast regulation of arterial blood pressure from chemoreceptors. When arterial blood level of oxygen becomes less, and when CO2 and H plus level higher, or simply you can say if there are hypoxia, hypercapnia, and acidosis. It stimulates chemoreceptors, send impulses that stimulate pressor neurons in medulla, and so it contributes to increase of blood pressure. And here you can have additional example. It's called the reflex to cerebral ischemia. Just imagine, even the general blood pressure is normal, even maybe in the sinus carotid area there is normal blood pressure, but somewhere inside the brain tissue there is some compression of vessel. It can be produced by tumor, by hematoma, by different reasons that mechanically compress vessel, and certain area, it can be thrombus, many things can be, and certain area of brain tissue suffers from hypoxia, and of course at the same time simultaneously there is hypercapnia and acidosis, and in this case central chemoreceptors respond by great activity, which strongly stimulates the pressor neuron, and you can expect that such a person can have extremely high level of blood pressure. Ischemia, I can remind you, this is insufficient blood supply, not corresponding to the tissue needs. And brain ischemia produces extremely high blood pressure because the central chemoreceptors respond to very high level of H plus ions and high level also of CO2, and it stimulates strongly depressor neurons. So pressure rises up to 200 millimeters mercury or higher. But you may understand that this is an important compensatory change, because under such a great pressure, blood supply to brain can become higher, and it produces at least a little bit decrease of excess of CO2 and hydrogen, and correspondingly a little bit increase the level of oxygen supply to this piece of tissue that suffers from hypoxia and other changes. Now we switch to the long-term regulation of the circulation. Again, I remind you that cardiac output, the heart function, and total peripheral resistance, the vessel's tone, is regulated by fast neural mechanisms. And the third factor was the volume of the circulating blood. With higher volume, clearly with the same parameters of both cardiac output and resistance of vessels, we can get normal blood pressure. Sorry, I was interrupted slightly. Let's move on. So the circulating blood volume, with change of the circulating blood volume, with the same cardiac output and resistance, we can have higher pressure, and with loss of part of blood volume, we can have less pressure. So this is steady change of pressure if blood volume is changed steadily. How blood volume can be regulated? As it was already mentioned, it depends on the functioning of the kidney. Fluid can be excreted by kidney in high amount and in less amount. So it can be loss of fluid predominantly, and water retention, fluid retention. Retention means more water remains in the body. This is retention. So, and mostly kidney are under hormonal control. And this most important mechanism of the regulation, long-term regulation of circulation, is due to Renin-Angiotensin-Aldosterone System. You see the first four letters make the abbreviation, which is widely known and studied many times during the course of physiology, and not only physiology. This is RAAS system. Renin-Angiotensin-Aldosterone, the three main sequential components of this system. And exactly, if you remember name and full, not abbreviation only, but full names, you can follow easily the sequence of events, sequence of secretion of these substances. Renin, then angiotensin, then aldosterone. This system operates beginning from decrease of pressure. Actually, we are going to study in future kidney function, and we again will deeply consider this system, and you will see that it's not the only one possible stimulus. But for today, let's start from the great decrease of pressure. Two arrows down show that it's not little decrease of pressure, it should be significant decrease of the systemic pressure, so that kidney blood supply may be decreased. In future, we will study that kidney blood supply remains constant within wide limits of blood pressure changes, systemic blood pressure. So, for real decrease of kidney blood supply, blood pressure should fall very low. And this is a stimulus, immediate stimulus for secretion of renin, decrease of kidney blood supply. As you remember from histology perhaps, the renin is secreted from juxtaglomerular apparatus cell, which is juxtaglomerular, located nearby the glomerulus, actually between the artery that brings blood and takes blood out of glomerulus. In this area we have the juxtaglomerular apparatus, and cells located around the bringing arterial produce, in response to decreased blood supply, the substance that is called renin. As it is secreted into blood, we can consider it as a hormone, but actually this is the protein that is the enzyme. And this enzyme splits one little piece from a big blood protein that circulates in blood constantly. This alpha-2 globulin, called angiotensinogen. Alpha-2 globulins, you see, globulins are largest blood plasma proteins, along with the fibrinogen. Globulins are very big proteins. And one of these globulins, from fraction of alpha-2, is called angiotensinogen, because exactly from this protein, the renin splits little piece, which is called angiotensin. But first, it's formed not active angiotensin 1. It consists of 10 amino acids. It's not active still, but further enzyme produces its activation. It's called simply angiotensin converting enzyme, ACE. And exactly under action of this enzyme, angiotensin 1 becomes converted into angiotensin 2. And it's just enough to split 2 more amino acids so that octapeptide is formed with 8 amino acids. And angiotensin 2 is powerful vasoconstricting substance. Angiotensin. Angio means vessel and tensin is clear tension. So, by the way, angiotensin converting enzyme is considered to be important in pathogenesis of hypertension, and many patients all over the world use the inhibitors of this enzyme to keep their blood pressure from elevation, to prevent elevation of blood pressure, because it's considered to be involved into hypertension. So we will study in pharmacology ACE inhibitors that produce block of this enzyme, and angiotensin 2 is not formed therefore. But it's not the end. Of course, angiotensin, according to its name, produces vasoconstriction. But this is rather fast effect. It's not through volume. Actually, we can say that this effect can be considered as intermediate mechanism. If we will not finish with this system, but if we reach this level, it's the effect that requires longer time than short-term or fast regulation mechanism, which operates within seconds or 1 minute or so. And of course, it's not hours or days as the full development of the effects of this system. Vasoconstriction is considered to be developed in about 20 minutes from the beginning of activation of the system. So it's clearly intermediate type of mechanisms, but it's not the end of the system. It's the urgent effect of vasoconstriction, but vessels cannot be kept constantly in high degree of constriction. And it already increases arterial blood pressure, but system operates further. Angiotensin circulating in blood reaches the adrenal cortex, where it stimulates the superficial layer, if you remember, glomerulus zone, where mineralocorticoid aldosterone is secreted under stimulation by angiotensin 2. And exactly due to aldosterone, we have finally an increase of blood volume, because aldosterone gradually, not immediately, starts to increase reabsorption of sodium, and each sodium ion reabsorbed takes along a certain amount of water molecules according to its water ions according to its osmotic activity. So the gradual process starts. Reabsorption of sodium ion by ion, molecule by molecule, but gradually after hours or especially after days, the aldosterone provides significant increase of the extracellular fluid volume, and blood volume correlates with extracellular fluid. It's a part of extracellular fluid. So blood volume becomes finally increased, which provides steady elevation of blood pressure even without vasoconstriction. Additionally, angiotensin 2 stimulates in the brain the thirst center, and this center stimulates, creates the sensation of thirst, which makes the person to drink water if it's available, and higher water intake makes faster restoration of blood volume, because of water becomes easily absorbed from intestine, from stomach even. So for kidney it's reabsorption, absorption back. For intestine, for digestive tract, for the stomach, it's simply absorption. The more blood is absorbed, the faster is effective restoration of arterial blood pressure. And so action of angiotensin can be stopped. It's not necessary anymore, because without vasoconstriction, with normal vessels tone, due to blood volume high level, we can maintain higher blood pressure. And notice that we started from great decrease of blood pressure, and finally we reach the opposite, arterial blood pressure elevation. This is Renin-Angiotensin-Aldosterone System. Look, renin, then angiotensin, then aldosterone are three main components. And again, renin itself has no effect. If you put drops of renin solution, for example, on the vessels, there is no vasoconstriction, nothing has changed. But when renin appears in blood, it finds angiotensinogen, splits the angiotensin 1, then a converting enzyme creates angiotensin 2, there is vasoconstriction. But vasoconstriction is not through volume. It's not fast. It's a fast or intermediate mechanism, not slow. And slow regulation or long-term regulation is then achieved through aldosterone. It's gradual higher reabsorption of sodium, gradual restoration of volume creates finally higher blood volume and therefore higher blood pressure. This is Renin-Angiotensin-Aldosterone System. There are some other hormones that also regulate blood pressure by changing of blood volume, and among the others, vasopressin is number one. It's a hormone that is familiar for you. You remember that it has two names, antidiuretic hormone and vasopressin, and it's secreted from the posterior pituitary, while originally it is produced in the nuclei of hypothalamus, nuclei supraoptic and paraventricular nuclei, mostly supraoptic. This hormone is produced due to following stimuli. First, if you remember, the main stimulus is the osmotic pressure increase, basically sodium elevation. Osmotic pressure increase means not increase above upper limit of norm, just within normal limits even. If you remember, the osmotic blood pressure minimal normal level is 280, 290 plus minus 10, so 280 milliosmol per liter. This is lower limit. And this level vasopressin is almost not secreted. But with any progressive elevation of osmotic pressure, by some millimeters mercury higher, vasopressin becomes secreted more and more and more. And it's 290, it's more produced, and 300 is even more, and then it goes up and up. And so, due to this, we naturally have no changes of the osmotic pressure in reasonable limits of water intake or something else. The second stimulus can be decrease of blood volume and great decrease of blood pressure, because they are separate volumereceptors and also baroreceptors. Usually when it occurs due to very quick, very strong decrease of blood pressure, or especially in case of hemorrhage, blood loss. So vasopressin effects are in high doses, as it happens due to response to hemorrhage or very, very serious decrease of blood pressure. There is vasoconstriction through V1 receptors. Vasopressin 1 receptors produce vasoconstriction. Notice vasopressin name is similar to angiotensin, because angion is the Greek root for vessel and vaso Latin root. Pressin, tension, there is no big difference. And two names make it easier to remember two effects of hormone, especially by activation of two different receptors. V1 receptors operate through phospholipase C pathway and IP3 in smooth muscles in vascular wall. But naturally, with lower doses, usually it operates in kidney predominantly through V2 receptors, and this hormone increases water reabsorption in kidney tubules. Therefore, it produces antidiuretic effect. Water retention occurs, less diuresis, more water remains in the body. And due to this, higher volume of the extracellular fluid becomes, and blood volume increases, and therefore blood pressure also. And it goes through V2 receptors that operate through adenylate cyclase pathway. And if you remember, it goes through insertion, due to phosphorylation, insertion of the aquaporins into membrane of tubules, of distal tubules and collecting ducts in the kidney. Another hormone is antagonistic to aldosterone, natriuretic. If you understand the word, natriuresis means loss of sodium with urine. Natriuresis. So while aldosterone produces reabsorption of sodium, stimulation of this reabsorption due to production of more and more sodium-potassium pumps. But natriuretic hormone is opposite. It contributes to loss of sodium. So also logically, it can be necessary only in case when we have excess sodium and excess of fluid. And natriuretic hormone also can be called atrial peptide. It's produced mostly by atria, but as well it was found that even ventricles and vascular walls cells can produce it, but mainly atria. And when atria are overstretched, when there is more than normal blood volume in the system, in the cardiovascular system. So it's clear that it operates due to negative feedback as well. Excessive volume stretches the atria more than usual, and atria produce more natriuretic hormone than usual. And excess of water will be lost in this case, because of natriuresis corresponds to loss of water at the same time. Sodium has its osmotic action on water, and water goes together with sodium out of the body. So total blood volume will be decreased in response of atrial stretching and natriuretic hormone secretion. So high blood volume, excessive blood volume stimulates secretion of this hormone. It has some more effects. First, clear from name, easily remembered. This is natriuresis, decreased reabsorption of sodium. And the resulting decrease of blood volume, it's clear because sodium is less reabsorbed together with less water reabsorption. But also, in a decrease of blood pressure. Also, it can stimulate relaxation of smooth muscles in vessels wall. So it creates higher volume for vascular system, which also contributes to decreased pressure. And also it inhibits renin secretion. But at least if you remember main effects, it could be very good. So, and this is the end of the systemic mechanisms of regulation of blood pressure. Don't forget that there are some local mechanisms, and local mechanisms are given in last pages of your text, and it's not very difficult, mostly descriptive. I hope you'll understand it easily. So thank you for your attention.